Hi, Mike. How are you?
Okay, I'm fine.
Thank you.
Awaiting your questions. Yeah.
Thank you, Mike, for having accepted another invitation on my YouTube channel, Scuola di Filosofia di Fornace. Today, we're going to talk about the wonder of water. This is the name of a book you published in 2017, and in which you describe the marvelous properties of water. In fact, the title is The Wonder of Water, The Wonder of Water.
It is a wonder. Yeah,
Yes,
okay.
yes, I read it. It is really a wonder. I strongly recommend to our public to read it. In fact, we often tend to underestimate the importance of water and to take water for granted.
Absolutely. Yep.
Let's think about it. Water is something, at least in the West, we always have in front of us, in our home, when we do sport, when we walk on the mountains, and so on. However, as you explain in your book, one should consider the special properties of or peculiarities of water, which are fundamental for the existence of vegetative and animal life form on Earth, but also for the circulatory system, for the climate, and so on. So, yeah. I think it's very important to reflect on this incredible element, considering, as you write in your book, the transcending fitness of water for life as it exists on Earth. That's why we're here today. So, a first very simple question is, what is water from a purely scientific, empirical point of view? So, water as an empiric element.
Well, water is composed of three atoms, only three atoms. Oxygen and two hydrogen atoms make up every molecule of water. And the actual basic formula of water leads to some of its special properties. One of the things about oxygen, for instance, is it's a highly electronegative atom. And it attracts the electrons from the water molecule, leaving the hydrogen atoms to be positively charged and the oxygen negatively charged. And this has the effect of, means that water is a highly polar compound. And in liquid water, it forms a vast hydrogen bonded sort of network. And that network gives water a lot of its curious properties. Water, for instance, boils at a very high temperature compared with other light gases, small molecule gases. And it freezes at a very high temperature as well. 100, it's zero centigrade to us, and it boils at 100 centigrade. And that's because the high melting point and the high freezing point of the boiling point of water is basically because of the hydrogen bonded network. It doesn't evaporate very easily because the hydrogen bonded network has a sort of a stickiness, and so molecules don't easily leave the liquid at the interface between water and air. So basically, there's the hydrogen bonded network, and this also gives it a very high surface tension compared with other fluids. Basically, it also gives it what is called the hydrophobic force, and that is the force which excludes non-polar compounds, like, for instance, the long chains, carbohydrate chains and fatty acids and fats from the aqueous phase. And it's the hydrophobic force which also causes the formation of the cell membrane, because the fats are excluded from the aqueous phase and forced into the membranes. The hydrophobic amino acids as well are forced into a tight ball in the center of proteins, causing the stability of proteins. So the hydrophobic force of water, which arises from its polar nature and the hydrogen bonded network, is a very important property of water. So basically, yes, it's just three atoms, and yet it has these different properties: high surface tension, high boiling point. It's got a very high evaporative cooling effect as well, and a high specific heat. And all of these things are related to this hydrogen bonded network. So some of these unique properties of water, which are very relevant, as we're going to see, to life on Earth, basically come about from its atomic structure. It's oxygen and two hydrogens, and the polarity of that molecule and the formation of the hydrogen bond creates a whole series of unique properties which are absolutely vital for life on Earth. But yes, to answer your question, it's just 3 atoms. And we're going to find out in this interview that these 3 atoms have a staggering amount of emergent effects in nature. And this is really beautiful. You just need 3 atoms and you get a whole lot of vital utility for life on Earth.
It's really, really incredible. So you talk about in your book about the marvelous properties of water, and also about the anomalous behavior of water. Water, you say, can exist in 3 different forms, in 3 different material states, but not inside the Earth, as it happens instead, for example, with rock, which melt into liquids, but within the range of temperatures and atmospheric pressures that exist on the Earth's surface. Water has also another anomalous behavior regarding its boiling and melting point. You also mention in your book other special properties of water, such as the surface tension and expansion in freezing, its viscosity, the importance of clay. Then you analyze the process of water eroding and weathering rocks. As capillary water, water can also be retained in the soil, ensuring the long-term supply of water itself and the nutrients for life, formation and distribution. So, can you talk about the importance of the hydrological cycle?
Oh, yes. Well, this is an absolutely wonderful, it's one of the great marvels of nature. You mentioned just a short time ago that water has the unique property of existing in 3 material states in the ambient conditions on the Earth. And it's the only substance on the Earth's surface which does this. What's the significance of that? Well, it means that, in fact, water can exist as vapor, as liquid, and solid on the surface of the Earth, right? And this is the key to the hydrological cycle. So the water evaporates from the sea and it goes from liquid to vapor. And then it rises in the atmosphere, it condenses, and it falls as rain. Or it falls as snow. And it forms rivers or glaciers, which in the case of rivers, they're highly mobile. The water is highly mobile in a river and runs back to the sea, so completing the cycle. And the glaciers, too, have, for a crystalline solid, a very, very low viscosity, and hence they flow back also, like the rivers, back eventually to the sea, or they melt and form rivers, and the rivers flow back to the sea. So the existence of water is as a vapor, a liquid, and a solid in the conditions that exist on the Earth allows this remarkable cycling of water from the sea, ultimately through the atmosphere, and then back again to the sea, onto the land, and then back to the sea. So that's what you call the hydrological cycle. This, of course, is vital to life on the land, because it's that cycle. It has little significance for aquatic life, which is living in the sea. But for terrestrial organisms like you and me and all other terrestrial life on Earth, this is a vital cycle because it delivers water to the land. Now, notice a very fascinating thing about this. So if you ask, what delivers water to the land? It's the properties of water itself. And this is beautiful. This is so parsimonious, so elegant. You don't need complex mechanisms or all this sort of stuff. Those 3 atoms do it themselves. They deliver themselves to the land for life on the land. It's very, very beautiful. So let's talk a little bit more about the hydrological cycle, because water doesn't just deliver itself to the land. It makes sure that life on the land, both vegetable and animal, can live. And why? Because, in fact, Water, of course, is essential as the matrix of the cell, the medium of the blood. It's essential to all life and certainly essential to all terrestrial life. But terrestrial life needs minerals. And it also, plants need soil. So how are we going to get minerals delivered to the land and soil generated? Well, thanks to water again. Water is a tremendous solvent, and its high surface tension, which you talked about earlier, draws it into the cracks in the rock, expanding the area for erosion and weathering. And then, of course, in the mountains and in the higher latitudes, it freezes and then it cracks open the rocks. So water acting on the rocks delivers effectively a whole suite of minerals to the land. And on top of this, it breaks down the rocks, providing sands and silts, which form the basis of soils. And why is that important? Because plants require water-retaining soils. That is micropores, a network of micropores formed in the soil. So water not only delivers itself to the land, it delivers also the minerals from the leached from the rocks to the land, and it makes soil from its erosional process as it tumbles over the various parts, as it tumbles its way back to the sea. And so it makes the soils which allow plants to grow and thrive, and plants provide the nutrients for animal life on the land. So water does everything. And of all the things I know about in nature, that is one of the most extraordinary facts that I'm aware of. Water delivers itself to the land, it delivers the minerals to the land, it makes the soil for the plants to grow. And if we want to just continue one more thing, you might well ask, well, plants are two forms. You can get non-vascular plants, which are things like liverworts and simple plants like that. And you can have vascular plants like trees and the plants that are growing in your garden and my garden.
Yes.
So how does the water get, though, from the roots to the top of the tree? Well, water evaporates in the leaves, and that acts as a draw in the water in the conduits which lead up to from the soil, from the roots to the leaves. Its high surface tension and its high tensile strength allow the water to be drawn all the way up to the leaves. So if you ask, well, how does water get to the leaves? Water delivers itself to the leaves by its own properties. And so not only does it provide the plants with the soils it needs, with all the nutrients it need, it allows photosynthesis in the leaves of plants, because it draws itself up to the plants, to the leaves at the top of the plants. Amazing. So water does everything. So life on the land depends on water, and one can go on, but nonetheless, that's the basic. That's the hydrological cycle, and it is a wonder of nature, and all that comes from the properties of three atoms.
Yes.
The whole.
Incredible, really, really. So I would like to ask you about the plate tectonics, because plate tectonics, for this dynamic, water is fundamental, even in this process, thanks to its role in lubricating the tectonic system. That's why you write, no water, no plate tectonics, no continents. Why?
Okay. Well, first of all, I just talked about water weathering and eroding the rocks, right? And clearly, if the rocks are not going to be replaced, terrestrial life has a limited lifespan. Because eventually the Himalayas and the Andes and all the great mountain chains, the Alps, will eventually be worn down. So that creates a problem. But they've been there for billions of years. So what's going on? Well, it's plate tectonics, and it's the turnover of the crustal rocks, which keeps elevating the rocks themselves. So plate tectonics is the key to why the mountains are not permanently eroded, because they're being continually thrusted up by plate tectonics. And guess what? Water plays a critical role in plate tectonics. Not just the hydrological cycle, it plays a critical role in the very process which erects those mountains, down which it erodes the soils and things for the growth of plants, the greening of the land. So in what way does it cause plate tectonics? Well, first of all, the mantle rocks contain water, which increases their decreases their melting point and decreases their viscosity, which makes them mobile. And it's the mobility in the mantle which provides the motive force for moving the tectonic plates and eventually throws up the mountains, right? The actual continental crust, which is the material we were talking about, the granitic crust, the light, buoyant material, which forms the continents, right? And that's upthrusted when the oceanic crusts subduct at what you call constructive boundaries, right? And so but what draws down the water into the mantle? So basically, I said, first of all, what I said there was that water gives mobility to the mantle rocks. And it's that mobility which moves the tectonic system, essentially, you know. But not only that, when the mantle extrudes at divergent boundaries, like in the mid-ocean ridges, it combines with water, forming the crust on the top of the moving plate. And that crust hydrates, and it's the hydration of that crust which eventually, when the plate subducts and pulls the crust down into the mantle, it pulls water down, which it combined with when the magma erupted, combines with water, and that water is eventually pulled down when the plate subducts into the mantle. So that's how the mantle gets its water, through the cycling of oceanic crust. And the actual motion of the mantle itself is also caused by water. So, and of course the erosion of the mountains and the rocks by water in the hydrological cycle deposits granitic material onto the seabed, and that is drawn down again to be recycled by the tectonic system. So you have a hydrological cycle, you have an oceanic crystal cycle, and you have the movement within the mantle. So, and all this movement, many of the key aspects of this are caused by water. Water is essential to the whole tectonic recycling system. So not only is water essential for eroding the rocks and guaranteeing water and minerals for terrestrial life, it's also, amazingly, it's also involved in ensuring that the tectonic system keeps cycling. And so that there's continual uplift of rocks at the constructive boundaries. This is complicated stuff and very difficult to sort of put quickly, but essentially, water's involved. Water is critical to the functioning of the whole tectonic system itself, and hence the uplift of the mountains. And then water is also doing the erosion of the mountains and so forth. Yeah.
And in fact, you comment that a design as such cannot be found in any artifact or machine ever created. A design as such. Okay. Starting from three atoms.
Yeah. Yeah.
It's incredible.
As Kant said, living things are reciprocally the parts of living things are reciprocally self-formative. And that's a good definition of life itself, actually. And yes, that's a phenomenon you get in life, which you don't get, I think, in any artifact. I mean, the parts of an automobile don't make the other parts or have any role in making the other parts. But in the cell, every part of the cell is reciprocally self-formative for every other part, you know. The DNA needs the proteins need the DNA, and so forth. Yeah. And in the tectonic system, it's similar. You have these great cycles, and they all each one depends on the other. For instance, the movement in the mantle, the movement of the mantle rocks depends on the oceanic cycle, bringing the water down its subduction to the mantle. So there's two sort of cycles which are, in a sense, yes, they're sort of self-formative. So it's quite interesting. Yeah.
Yes, it's like a chain, like a logical chain, a natural chain.
Yeah, it's beautiful, and I think Kant was the first person to actually mention that life exhibits a reciprocal self-formative phenomena in living things. Yeah. And yes, and in a sense, the tectonic system also has aspects of that as well. Yeah. Like, one part of the cycling is dependent on the cycling in another part and things like that.
So I would like to talk about the oceans, because oceans, so always water, always water, are causally a priori to almost everything else on the Earth. Tectonic recycling, continental crust, mineral content of water, soil and plants on land. Water is also important in order to protect the Earth from long-term temperature deviations over billions of years and to preserve the oceans. There is a negative feedback regulatory system which acts regulating the amount of CO2 in the atmosphere. Can you talk about that?
Yes.
Okay.
Yep. Yeah. This is the phenomenon of silicate weathering. When the temperature rises or CO2 rises in the atmosphere, weathering increases. And the effect of that is to draw CO2 from the atmosphere into bicarbonate, which is deposited in the oceans. And vice versa. If the temperature goes down and the CO2 goes down, silicate weathering is decreased. So this is a perfect feedback system for maintaining the temperature and CO2 levels in the atmosphere. And that has had a long-term effect, of course, of preserving the oceans, because maintaining the temperature of the Earth and the CO2 levels within a certain level has the effect of maintaining the oceans and the Earth, actually. And there's other things, of course, which you could talk about. For instance, you're probably going to mention the cold trap, because yeah.
I come now to this point, but please, if we want. Okay.
No, that's okay. The silicate weathering is a beautiful feedback system because, of course, most of the rocks in the Earth are silicates. So they're not rare; they're there all the time, and so basically, this system operates really all the time. Yeah. So it's continually operating. Yeah.
The next property.
But there's one other plus we should. There have been times in the past called snowball Earth, when it seems that in fact the ice was ice right across most of the oceans, and of course because of that there could be no silicate weathering, and that means that all the CO2 coming out of volcanoes was left in the atmosphere to warm the Earth and melt the ice in the snowball Earth phenomenon. Yeah. Anyway, sorry, continue.
No, it's perfect, because the next question was about the impact on climate generated from water. So the expansion on freezing, which avoids the Earth to become something like a snowball. And the question was about the cold trap, in the troposphere, avoiding water to ascend too much in the atmosphere and to be dissociated in hydrogen and oxygen, with the hydrogen which would then be lost in space, as it happened to Venus.
Yeah. Well, first of all, the fascinating thing that water has a maximum density at 4 degrees, okay, and seawater I think is 1.8 degrees, right? And this, of course, prevents water from freezing from the bottom up. And also, of course, ice. Now, the fact that ice is less dense than water, and the fact that water has this maximum density at 4 degrees, both these phenomena arise from the hydrogen bonded network. And they're unique. They're pretty well unique to water. Very few. I think there's one or two other compounds expand on freezing. I think gallium is one of them, but I think that I'm not aware of any liquid which has this curious situation when you keep decreasing the temperature of the water, and the density keeps increasing, but then at 4 degrees it starts decreasing, leaving the density maximum at 4 degrees, which means that the surface water at 0 degrees is less dense than the water at 4 degrees. So that prevents water from freezing from the bottom up. So that's very interesting property of water. Now the next topic you mentioned was the cold trap. Yeah.
Yes.
That's it. Yes, because as you ascend in the atmosphere up through the low level of the atmosphere, the troposphere, which goes up to about between 13 and 18 kilometers above the surface of the Earth, the air gets less dense, contains less matter, contains less water to absorb heat. And also, as you probably know, if you ever let the pressure out of your car, you'll feel it. It's very cold because as the air expands, it cools. It's called adiabatic expansion, the cooling of adiabatic expansion. And that is also playing a role, I think, in cooling the atmosphere. But there's a whole number of factors then. There's less matter to absorb the heat, there's less water, it's got a lower, the atmospheric pressure is lower, and so forth. All these factors cause a cooling as you rise from the surface up towards the top of the troposphere. And so this creates a cold trap because the temperature in the troposphere is below the freezing point of water. So this means that as water vapor arises, instead of going through the top of the troposphere into regions of the atmosphere where it would be broken down by UV radiation and such like, it freezes and falls back to the ground as rain or snow. So the cold trap at the top of the troposphere prevents the loss of water from the Earth because it prevents water going into the higher points of the atmosphere where solar radiation breaks it down into oxygen and the hydrogen is lost to the Earth. Okay, it's lost to space. So the troposphere, the cold trap at the top of the troposphere, prevents water being lost to space. And so that's another very important feature of the design of the Earth, which holds water on the planet and holds the oceans as they are. Yeah.
And then, Mike, after the technical and the scientific questions, I would come to a philosophical one. Because in your book, quoting Paul Davies, you write that all special peculiarities of water do conspire toward an overwhelming appearance of design. In The Wonder of Water, you write many times about teleology, intelligent collusion of water's properties, teleological pattern, irrepressible sense of design, and so on. Can you comment a little bit about the idea of a design regarding water? Because you already gave us some considerations, but some more peculiar considerations about the design of water.
Yeah, well,
I know it's difficult. I know it's not easy.
Oh, no, it's okay.
No.
Well, basically, for me, I mean, I would go back again to the hydrological cycle. Okay, because basically, what you have there. I mean, if you want to ask me why do I think it certainly looks as if there was a designer behind the properties of water. Okay, first of all, what you have in the hydrological cycle is a series of a sort of a causal hierarchy. Okay, for instance, the erosion of the rocks depends on the prior property of water to have the three, to be water, vapor, liquid, and ice. In other words, the erosion of the rocks depends on the previous property of water, and that is to form the hydrological cycle. And then you come to the the soils. The soil is dependent on the erosion of the rocks. So you get a sort of a hierarchy, a beautiful hierarchy where one phenomenon is dependent on the previous phenomenon and so forth in a sort of hierarchy. And that, I find that is really an amazing fact about the hydrological cycle. And also the fact that water delivers itself to the land, I find that just so clever. And I find it so clever the way water ascends to the top of a tree. I mean, I'm overwhelmingly struck by the fact that this seems to suggest some sort of design behind the world. Not any design, but a design basically for a world like ours. Okay, because when you look at the properties of water from its fitness for the cell, the hydrophobic force forming membranes and things in the cell, and you look at its fitness for the circulatory system, you look at its fitness for plate tectonics, you look for its fitness, as we say, for the hydrological cycle, for life on the land, and so forth. You think, well, for these three atoms, for this world of fitness to emerge from these three atoms, this fitness must have been envisaged by whoever designed. This is going on from design, right? I mean, it looks like design anyway, but that design involves so much of what we see on Earth that it strikes me as that whoever designed the properties of water had a world like our world with beings like us in mind. So that the planet Earth and life on Earth, terrestrial life like ourselves, right, was already envisaged in the order of things from the beginning. And I find so that it's not just I do see that it strikes me spontaneously and automatically that this looks like design, and it's a design for a world very like ours because the properties of water are so diverse, plays so many critical roles in so many things. We didn't mention, for instance, endothermy. I mean, endothermy is we're warm-blooded organisms, and endothermy depends on three properties of water. It's high specific heat, which is higher than most common fluids. It's very high cooling effect on evaporation, and it's high conductance of heat. And the cooling effect of evaporation of water is the highest of any molecular substance. So it's extraordinary, right? And these are the three properties of water you need if you're going to be endothermic. That's the prior fitness you need for endothermy. So it's not just life on the land. It's so intimate. The fitness of water for our being is so intimate, actually. It's quite extraordinary. I think I've mentioned in other interviews, actually, that when I was thinking about, for instance, how we lose heat in the body. Well, first of all, you need a circulatory system to get rid of the heat from the tissues to the skin. What gives you the circulatory system? Water. And how does water take the heat to the skin? Well, it's got a very high specific heat. Wow, that's good. That's convenient. When it gets to the skin, it evaporates, causing the highest cooling effect of any fluid. Now that is, it's not just that water gives you endothermy, it gives you the way of getting rid of it in different ways. As a fit medium for the circulation, and as the fittest medium we know for cooling the skin when it evaporates and so forth. So anyway, I always like bringing in endothermy because it is really quite amazing. So water gives us our endothermic state, and water allows the heat generated by endothermy to escape the body. QED.
Incredible.
Quite easily done. It's brilliant. And that's and it's the brilliance of these specific designs, just like the one I've just mentioned, but there's many, we've already discussed them already, but it's the brilliance of these specific designs for the end of life on Earth, which convinces me that it's there by design, and it's not just any design, it's beautifully parsimonious. You don't need anything complex. I think that there's a famous quote by Newton, which he said that, I can't get this exactly right, but Newton said, nature prefers simplicity and abhors superfluous causes.
It comes from Aristotle, in fact, from Aristotle.
Does it?
Many
Okay.
centuries before, long ago, from
Also,
Aristotle.
Newton was a plagiarist. Yeah.
Yeah, in his writings about nature.
Did he really? I didn't know that. I knew the Newton quote, but it comes from Aristotle.
Yes, it's Newton, but it was said centuries ago by Aristotle, and then it was inherited by the Christian authors like Saint Thomas of Aquin and so on.
Right. Well, we know
it was said in Latin, natura nihil frustra facit, which means nature does not make anything in vain, from Latin.
Okay. Beautiful. That is very, very beautiful. Well, neither Aristotle nor Aquinas knew about water.
Yeah.
So their views, which were based on belief or philosophical ground.
Aristotle did observe nature because he was a very good observer. Of course,
oh, yes.
He didn't have the instruments we have, the scientific instruments. He didn't have them, but he was a very good observer.
Okay, but certainly the properties of water, as we now understand them,
yeah, of course,
wonderfully confirm what I would tend to call intuition about the way things are. Okay, so modern science here in the properties of water has confirmed that intuition, that nature abhors complexity and superfluous causes. Anyway, sorry, so I got that wrong. Actually, you correct me. I thought, well, so Newton didn't. I don't think Newton acknowledged the source, but perhaps it was so common to Western intellectuals that he didn't need to.
Yes. Because it was a general philosophical comprehension that nature did always choose the simplest way to do things.
Yeah,
this was the common belief from ancient times to modernity.
Well, the way the hydrological cycle works is the most perfect example of that.
Yeah,
water delivering itself to the land and doing everything else you need for land-based life.
And in fact, I would say that that there is the fine-tuning argument, and we always present it in the field of cosmology, for example. But I would say that fine-tuning does also regard water, not only the physical constants and forces in cosmology and in physics, but also water.
Of course, yes. And the fine-tuning evolves. If you want to do any more of these interviews, right, the next one should be on the cell.
Okay.
You might. I wrote a thing for the DI, which was published a few weeks ago, about this short article, right? But yes, I mean the fine-tuning of the four basic atoms which make up biomatter: carbon, hydrogen, oxygen, nitrogen. The fine-tuning of those properties for the carbon-based cell is so astonishing that it's virtually a blueprint for the cell. I mean, basically, and in fact, what it really means is it doesn't really matter what steps led to the first cell, whether it was Darwinian, Lamarckian, special creation, or what have you. The blueprint for the cell was written in the properties of those four atoms in an astonishing way. But that's something to talk about, in another interview if you want. But basically, the fine-tuning of the properties of matter for life as it exists on Earth, I think, is every bit as amazing as cosmological. But it's much closer to home. I mean, if you say you're sitting there breathing at the moment, you can only breathe because oxygen is a gas. Okay. And you can only breathe because carbon dioxide, the end product of oxidation, guess what, is also a gas. So you can use the same organ to take it in and get rid of it. And not only that, the carbon dioxide combines with water to form a buffer called bicarbonate buffer, which is just the sort of buffer you need as an air-breathing organism. So basically, just sitting there now, you're experiencing, as you breathe in and out, some of the fine-tuning for advanced organisms like us, which require oxidations to give us the energy we need, metabolic energy. So yeah, so basically, the fine-tuning in biology is more intimate. You know, it's more, it directly applies to us. The fine-tuning of the cosmological constants could, anyway, be for all forms of life, all sorts of different forms of life you could imagine. At least it's certainly, the cosmological constants do mean stable planets like the Earth will occur and solar systems will be stable. You know all this stuff, this is your area. But basically, it's the biological fine-tuning which is close, it implies that the universe was designed for beings like ourselves. Whereas the cosmological constants mean it was designed for stable planets, for some of the basic conditions for life, but not for the specifics of life as we see it on Earth. But certainly there is an enormous amount of fine-tuning in the biological constants for life as we see it on Earth. Yeah.
So there is a very interesting point in your book about cosmology, about astronomy or cosmology. And this could be, if you agree, our last question for this interview. So nowadays, the NASA is researching on the so-called ocean worlds, which are planets which contain a substantial amount of water. If I if I remember, it should be 50% of water, so the ocean worlds. And you write very correctly that water is also important in order to create new planetary systems and also habitable planets.
Yeah, yes, that is something I got from, there is an astrophysicist, you might know who, it's Leyden. I've forgotten her name. I can't give the name off the top of my head, but she has written some papers about the importance of water in the formation of solar systems and planets. I mean, it's quite remarkable. Apparently, one of the things that do is water acts as a glue to stick cosmic dust together, and that the gluing of dust is the first step towards the coalescence of matter into planets and things like that. And certainly, she also mentions the fact that back again to the thermal properties of water, it has a cooling effect apparently, which also promotes planetary solar system and planetary development. But I mean, I can't expand on that. It's not my field.
Okay.
I just, yeah. But basically, she's at Leiden, and she's a professor of astrophysics at Leiden University or Leiden Observatory, and she has written about this as well. But I mean, I've only read her papers, but I'm sure her papers are one of many from other astrophysicists about the importance of water. So, so yeah, so we need water to get a planet now.
Yeah.
Not only do we need it for plate tectonics and hydrological cycle and the circulation and endothermy. And so
water is fundamental in biology, cosmology, chemistry, physiology, and so it's very an astonishing subject matter to study. So I strongly recommend once again to our public to read your book, The Wonder of Water. So, Mike, there are other very interesting properties of water we didn't discuss, not because it's not interesting, but because it will require a very, very long amount of time to do it. So your book is there, one can read it. I think you write it also, I wouldn't say in a simple way, but in an understandable way, even for non-experts, giving also examples, many quotations, and so on.
Yeah, I hope so. It's anyway, yeah. Well, once you've written a book, you can't go back.
Yeah.
So
Okay.
yeah,
Okay.
yeah,
It's true.
yeah.
True.
All I can say is that, in fact, yeah, it's a. I think that book does contain, though, the great majority of phenomena uh, in which water is vital for life. I think it's pretty comprehensive
Yeah.
because
I agree.
I'm always thinking about these things, and I don't think I've found many major omissions. I think that it mainly covers most of it, actually. Yeah, yeah.